Hello, my name is Nabil Sadegh. I'm a software developer specialized in high-performance graphics, rendering, and artificial intelligence. I'm also the co-founder of Nakorm and Zsoft, a company specialized in AI and innovative technologies in the AEC industry. Today, we'll be talking about developing AI pipelines for reliable, outcome-based BIM. And today I will be doing that with Candice, and I will let you, Candice, introduce yourself.
Hello everyone, I'm Candice Hassin. I work for DB Lab, a software company specialized in BIM data management. Artificial intelligence is not just automation. It's about augmenting our capabilities, expanding our knowledge, and unlocking new possibilities. It promises better decisions in a world facing immense challenges: climate resilience, health and safety risk prevention, designing buildings that boost professional performance, and enhancing everyone's quality of life. Our goal today is simple: to give you practical, actionable keys for building AI systems you can trust. We'll cover three parts. First, context and questioning, framing the right problems so your AI delivers the outcomes you need. Data, ensuring your inputs are clean, robust, and fit for purpose. AI capabilities framework and architectures for practical outcomes. Let's begin with the transformative power of AI. AI is multimodal, combining text, speech, images, and sensor data. AI is also multi-scale, from precise tasks like placing biomedical equipment in a BIM model to broad ones like parsing contracts. Its adoption brings both organizational and technical complexity, and it's evolving at breakneck speed, reshaping competition everywhere. Most importantly, AI is changing human-machine interaction itself. As we humanize machines, we redefine how decisions are made and where responsibility lies. Now, let's look at what this transformative AI power means for BIM. At a high level, AI enables us to generate BIM models from any data, automating what used to be manual. Enrich those models with semantic insights, adding metadata, classifications, and compliance checks. Analyze them continuously, performing clash detection, performance simulations, and predictive maintenance forecasting. And it's all made possible by Autodesk Platform Services, which provides seamless data accessibility and limitless integration capabilities. But before doing that, we have to identify why we want to do that. The why. The why is about identify the root cause of the problem you're solving. Dig deeper in the real problem. Clarify what's known and what remains unknown. Assess the level of impact that problem has on your business and operations. And define the target outcome you want to achieve. The outcome sits at the heart of everything. It's a bridge between your high-level strategy, missions, value, objectives, and the day-to-day operations. capabilities, and metrics. It tells you why it matters in practical, measurable terms and guides every technical and organizational decision you make. With that outcome in mind, you then answer 4 critical questions. Who are the stakeholders and end users who must buy in and benefit? How will the process and technology work together to deliver the outcome? What specific deliverables or outputs will drive you toward that outcome? And when will each milestone occur? And how will you measure progress? Nail down this question upfront, and you ensure your data and AI pipelines don't just run, they deliver real value. And now I'll hand you over to Nabil, who will dive into the critical role of data in making these AI pipelines a reality.
Thank you, Candice. So let's begin with what underpins everything we do with AI in BIM, the data. BIM data comes in many forms: geometric data derived from 3D models, point clouds from scans, alphanumeric metadata, such as material specifications and spatial dimensions, as well as collaborative annotations, design notes, and exchange files. Together, these elements form a rich digital ecosystem. This ecosystem feeds and shapes the AI systems we build. And the reality is simple. The quality of AI output is entirely dependent on the quality of input. If the data behind your BIM model is inconsistent, incomplete, outdated, or difficult to access, it creates uncertainty. It leads to flawed predictions, questionable insights, and sometimes even rework in construction. We often say that AI is not a magic wand, it's a mirror. It reflects the quality of the data it is trained and fed with. To get value from it, we must treat data as a strategic asset. That means structuring it properly, cleaning it consistently, and enriching it with context. And this isn't something that happens after design. It must start at the authoring level, when the first lines are drawn in a Revit model, or the first elements are tagged in AutoCAD. The tools we work with every day, whether it's Revit for modeling, AutoCAD for drafting, Autodesk Construction Cloud for collaboration, or BIM Collaborate Pro for coordination, are not just platforms to produce deliverables. They are environments where data is created, shared, validated, and ultimately used by artificial intelligence. As we build AI pipelines, we treat these tools as both the data source and the data interface. Integrating AI into these platforms allows us to maintain fidelity and real-time feedback. This enables AI systems to access what they need when they need it and present it to the right stakeholder in the right format. But what do we mean by reliable data? Internally, it must be logically sound. There should be no contradictions between components or attributes. It must be complete, meaning that all the information needed to make a decision is present. And it should reflect real-world conditions, not assumptions. Externally, reliable data must be interoperable. That means it should travel seamlessly across platforms, teams, formats, and tools. Industry standards help make this possible, but it also requires human diligence and digital discipline. Building data pipelines that regularly check for integrity and compatibility. Now, consider the data sources we rely on. It's a diverse collection. High-resolution laser scans, drone imagery, existing CAD drawings, IoT sensor streams, regulatory and compliance documents, or even past project archives. The first challenge is aggregation. But more important is transformation. We must move away from raw, scattered information to unified, structured, and machine-readable data. This is where we go beyond traditional ETL, extract, transform, load, into intelligent classification and collaborative context building. That's the groundwork artificial intelligence needs to operate effectively.
To wrap up our section on data, I'd like to highlight that AI's role in BIM is to transform data into intelligence via two key points. Why move from data to AI? BIM generates ever-growing volumes of information, and AI finally lets us put it to work. Why now? AI is advancing so rapidly that BIM applications are becoming accessible, and we need that power more than ever to elevate our work quality and deliver the best results. Now, it's time to explore the heart of our topic, AI technologies.
Yes, so now let's talk about the role of AI in BIM. To make this journey more intuitive, we'll explore AI technologies through a human lens by comparing them to human abilities. Just as we rely on our senses and cognition to interact with the world, AI mimics those same abilities to interact with data. We look at how AI can see, hear, speak, understand, act, learn, reason, and even retrieve and generate information. For each of these abilities, we'll briefly define the AI technology, explain the type of inputs it uses, and then walk through specific use cases. We start with the ability to see, powered by computer vision. Computer vision allows AI to interpret visual inputs such as images, video feeds, 3D scan, and the BIM model itself. In the BIM context, this often means data from drones, high-resolution cameras, and LiDAR systems. These tools provide AI with a detailed view of the construction environment in real time. With this input, AI can detect visual discrepancies between the BIM model and on-site reality. It can also flag structural deviations, missing components, or early signs of defects. Other use cases could include automated quality control, model compliance verification, and real-time monitoring of construction progress. We've talked about the ability to see. Now let's talk about hearing and speaking, achieved through speech-to-text and text-to-speech technologies. These enable AI to convert spoken word into text and text into spoken word. Input comes from microphones, meeting recordings, voice notes, video calls, conversation, and in practice, this helps convert, for example, inspectors' verbal observations directly into BIM model annotations. It supports hand-free interaction with BIM tools on site, and enables virtual assistants to read back information from the model. The result is smoother data capture, better communication, and reduced manual transcription. Understanding language is another crucial ability. This is where natural language processing, or NLP, comes in. NLP allows AI to analyze and extract meaning from large volumes of textual data, such as specifications, contracts, compliance codes, and inspection reports. Input sources include scanned documents, digital reports, emails, and logs. The AI can automatically check, for example, model data against regulations, or identify compliance issues and generate reports. These capabilities are invaluable for automated compliance verification, risk identification, and document summarization. Next, we have acting in the world. That's the domain of robotics and automation. With this technology, AI doesn't just analyze, it performs physical and virtual actions based on BIM data. Robots and drones equipped with sensors can interpret 3D models and execute tasks such as component assembly or structural inspections. The data fed into these systems often comes from the BIM model itself, as well as real-time feedback from the site. Key use cases include automated prefabrication, on-site material handling, we have autonomous inspection, improving speed, safety, and precision. Then we have the ability to learn, enabled by machine learning. Machine learning allows systems to analyze past data to predict future outcomes. Inputs include historical project data, sensors readings, weather conditions, and budget records. AI identifies patterns and correlations to forecast risks such as delays, safety incidents, or budget overruns. It is used for proactive planning, predictive maintenance, and cost estimation, helping teams make better decisions based on real evidence. Reasoning is perhaps the most sophisticated human-like ability AI is beginning to replicate. Logical inference involves making decisions based on structured logic and known relationships. The inputs here are complex data sets, BIM models enriched with constraints, dependencies, and performance requirements. AI applies rule-based systems to identify and resolve clashes, optimize layouts, or select the best fit design scenarios. In BIM, this translates into smarter, faster decision-making during design coordination and model validation. Each of these technologies, vision, voice, text, robotics, prediction, and reasoning, works best when orchestrated together. They relied on shared data environment, coherent workflows, and ongoing feedback loops. AI isn't a single product, it's a system of systems. And one especially powerful innovation is retrieval augmented generation, also called RAG. In plain terms, this means AI doesn't just guess based on training data. It actually retrieves the most relevant real-world content from BIM databases, past project files, regulatory references, and incorporates that into its response generation. It's like having an AI that both understands and remembers. RAG-powered tools can suggest which materials to use based on both compliance and performance. They can draft documents, they can answer questions contextually and with reference to your actual data.
We have so many possibilities, but before analyzing practical examples, I'd like to focus on AI in the building life cycle. From design through construction and operations, every phase involves decisions and tasks, approving scopes of work, authorizing trades, ordering materials, scheduling maintenance. Behind each decision is a data pipeline with stages: acquisition, processing, analyzing, visualization. And each stage manages specific inputs to deliver useful outputs. To unlock AI's full potential, this end-to-end pipeline must live both in your technical architecture and in how you share insights with stakeholders. That's what makes AI-driven decisions trustworthy, transparent, and repeatable. And now, let's move on to some architectural examples.
So let's start with this first architecture of AI architecture for defect detection. Now, this might look complex, but we'll go through it step by step. So first, you can see in blue several AI technologies that we have seen previously: speech to text, RAG, augmented generation, machine learning, computer vision, NLP, natural language processing, reasoning, and automation. In black, you can see inputs, several inputs, and you can see that every input goes into one AI system, and this AI system will extract information from this input before feeding this new output into another AI system or delivering that through outputs to the end users. So if we look at, for example, the speech-to-text system, it gets information from meetings, instructions, recordings in general, transcribe them, feeds this transcription text into an NLP model, natural language processing, that will then extract information from this text. This information then goes into a reasoning system that combines the outputs of several models to be able to detect clashes and make informed decisions. Let's look at, for example, the computer vision part on the right side. The computer vision takes laser scanners or drone outputs as an input, extract meaningful information, actually extract data from images, and then again feeds this into the reasoning model. Let's have a look at one more, machine learning, for example, which take IoT sensors data or BIM tools such as Revit or APS. Again, find patterns to extract information and feeds that into the reasoning model. The reasoning then, with all this information combined, will be able to detect clashes and make informed decisions. Once this information, this new data, new output is generated, it is sent at two different places. One, a dashboard, which acts as an output that can then deliver information to the final users, such as project managers or clients. It also sends information to the automation module. The automation module will be able to act or give acting proposition that can then be applied to the system, to the BIM model, or to the real world construction site. This is done through reports and notifications that are then received by architects, engineers, contractors, or field workers. Let's have a look at a smaller and maybe less complex example. AI-driven BIM update for digital twin synchronization. Synchronizing digital twin, making sure they're up to date and they match real world data is time consuming. It's a very long process. So with this architecture, we can start with the BIM model itself, stored in Revit. This BIM model will then feed a computer vision module to be able to extract valuable information from the BIM model. Laser scans and point clouds will also go into this computer vision module that will also extract information. And all this information falls into a reasoning module. The reasoning here is for consistency checking and is for denoising all this information. The reasoning also takes IoT sensors and extract again information, combines that with the computer vision output. All of that is then fed into a machine learning model to find, detect pattern, and give updated predictions. This is then applied into the BIM model to be able to update the model itself and make sure it's synchronized with real world information. On the other side, we have a similar pipeline. We start with text and voice data, reports, logs, etc. This goes into a speech-to-text and natural language processing module, which will convert any call, any recording into text, and will extract information from this data. This then goes into RAG, Retrieval Augmented Generation module, which will be able to, using this data and the BIM model data, search with context into historic past databases or compliance information or any other report document. And this will then detect any differences, any modification that happen in real life that has to be mirrored into the BIM model.
Integrating AI into BIM is a holistic journey. In conclusion, we focus on 3 keystones for success. Technical foundation: automate the routine, but architect the future. Business momentum: prove value fast, then scale with confidence. And finally, the legal keystone: governance and responsibility. Empower machines, preserve human expertise, ensuring humans remain in control of decisions.
Thank you very much for listening to us.